Suppose you need to predict how someone is getting to work. Maybe they can take a car, a bus, or a bicycle. Linear regression isn't really going to cut it anymore, because you need to predict a category. Let's look at a simple example involving authorship attribution in the Federalist Papers. These 85 documents were written by Alexander Hamilton, James Madison, and John Jay in support of the proposed United States Constitution during 1787 to 1788. While all written under the name Publius, different men authored different articles. Historians know the primary author for most of the documents, but 12 of them are disputed between Hamilton and Madison. We want to develop a simple model from the known documents to predict who wrote each of these disputed documents. This diagram here is just a general idea of what the documents might be. You've got these blue ones representing Hamilton, these green ones representing Madison, and a few purple ones representing Jay. For features, we're going to stick with something simple, relative word frequencies. So if the word upon occurs 10 times in a document with 1,000 words, we assign that variable a value of 10 divided by 1,000 equals 0.01. By computing this for every word that occurs in any of the documents, we can create a vector of variables ranging from 0 to 1 for each document. Here's a simple example sentence. The rocks in the river down in the valley. If you color each unique word, you can then compute the relative word frequencies. There are 9 words. The word the occurs 3 times, so its relative word frequency is 1/3 or 0.3333. The word rocks occurs once, so its relative word frequency is 1/9 or 0.111 repeating. The word in occurs twice, so it's 0.2222, and river, down, and valley all occur just once, and so their frequency is 0.1111 each. For this dataset, we're removing all punctuation and ignoring case. A script that created the data is available as countwords.py that ran on a copy of the Federalist Papers from Project Gutenberg. Suppose we have some word frequencies in a simple table like this. How do we use these to pick the author? We can see that Hamilton happens to have 0.6 relative word frequency of use of upon, which is quite a bit, whereas Madison in doc number 2 has 0.5 relative word frequency for R. Finally, there's document 3, which is disputed, which has its own relative frequencies that seem to lie somewhere between Hamilton and Madison. You can imagine using these word frequencies then as our base features, computing some weights, and trying to do something. If you only had 2 authors, you might try linear regression, setting your target variable to 1 for Hamilton and 0 for Madison. You'd have to set some threshold, maybe 0.5. If your predicted value exceeded that, you would vote Hamilton. Otherwise, you would say Madison. Here's a simple graphic to help illustrate this. If we were only looking at the relative word frequency of the word as versus some computed score that we created with it, you could draw a line on the score, above which it'd be in the blue zone here for Hamilton, and below which it would be in the green zone here for Madison. And this would also correspond to some threshold of the word as if that was the only variable. But this isn't totally responsible. What does it mean if the model predicts a value greater than 1 or less than 0? And how can we add more possible authors? What if we computed a score for each document for each author? Then the author with the best score should win that document. And winning by more should make the model more confident. So what we really want are probabilities for a given document belonging to the authors. For this model, we're assuming the documents had to be written by one of these 3 authors, so the probabilities must sum up to 100% in the end. Let's start with a simple linear model to score a document, and suppose that we already have some weights. Here's a very simple equation using the word frequencies from the words as, are, and upon. So that Hamilton has weight 2 for word frequency as, weight 3 for word frequency are, and weight -4 for word frequency upon. These are completely made up, so don't worry about this being a good model or not. And you can see there's another score that we'll compute for Madison, and the third score we compute for Jay, again using the frequencies all of a single document to compute these 3 scores. Maybe it's reasonable to assign a probability based on the fraction of score for a particular author. So if Hamilton has a score of 10, Madison 5, and Jay 5, then Hamilton should have 50% probability, while Madison and J would have 25% each. So the equation would be something like the probability that this document belongs to a given author is that author's score divided by the sum of all scores, where A here represents which author. This has the necessary property that the probabilities add up to 1.0, which is equivalent to saying one of these options must be the author. But what if SH happens to be a negative number? Then we'd compute a negative probability. There's something going wrong here. To correct for this, and for other reasons, let's instead restrict the scores by using an exponential function. So take our previous linear function for Hamilton, and now we're going to make that the power of an exponential e. E, recall, is 2.71, etc., etc. So now each score must be positive, and we can still compute the probability as the share of the total score. Your score now is just this funny e to some linear function. This is known as logistic regression, or multinomial logit model. You'll also hear it called a softmax model. In the case where you have only two classes, you can basically fix one of the scores to 1.0 and just score the other class, because if it's not class A, it must be class B. This simplifies the probability to 1 over 1 plus e to some linear function, and note the negative 1 that goes in front of this. You're sort of computing it not being A versus B. Don't get too hung up on those details though. This is called the sigmoid function. It will be coming up later in another context. Don't worry about it too much now, other than it restricts the output to be between 0 and 1. Now let's do a little Python to get familiar with this data and just get comfortable with these functions. We're going to import numpy as np just as we did before. However, we will also import math to get access to the exponential operator. You can do this other ways, but it's helpful just to use a standard library and get comfortable with it. Data for this is in fed.npz, which we'll use numpy.load to get at, and it again is just a single array, so we'll load that in. Here, the authors are in the first column, so you say colon for all the rows, comma 0 to get all those columns. The word frequencies are stored by most common to least common in order. So let's just grab the relative word frequencies for each document with the colon, comma 1 through 4, so the first 3 columns of relative word frequencies. Now let's make up some weights for each gentleman's score. The linear part of the weight here for Hamilton is then 2, 3, negative 4. For Madison, it will be a numpy array of 1, 5, 1. And for J, suppose it's an array of 4, negative 2, 1. Again, these are just fictitious values that do not matter. Now we should define our logit function so we can compute the probabilities or compute the scores of each gentleman. To do this, we input our relative word frequencies, and then we use those to compute each score. First, we say Hamilton's score is math.exp. We're going to raise that to the power of his computed score. We can take his weights and dot them with the given freaks because they're all numpy arrays. And we'll do something similar for Madison and J, just changing the variables as appropriate. Given their scores, we compute the total score by just summing them up, and then we can just return each score as that particular author score divided by the total. A quick list comprehension will bring up the probabilities. You apply numpy array, we'll make a list. We'll just call this logit function on each of the documents that we have. Keeping in mind we've already pulled out only the first 3 variables. Now we have probabilities. We can have a simple for loop here to look at the actual authors versus the computed probabilities. We'll use zip to attach the list of authors to the list of probabilities. Here 0 encodes Hamilton, 1 encodes Madison, 2 encodes J, and 4 encodes disputed or unknown author. Probabilities are all just made up. You should just see that these probabilities all just sum to 1. Try fiddling around with different weights and features to see if you can improve the model. Think about if it makes sense to even include John Jay, given that he wrote so few of the papers and he's not considered historically to be a contender for these disputed papers. Okay, now you've got the basics of logistic regression. But let's see how we can simplify this process and do some actual training using Keras.